In this video, we're going to continue our discussion of power series functions. Starting with a geometric series summation n equals 0 to infinity x to the power of n is equal to 1 divided by 1 minus x for absolute value of x less than 1. That means the radius of convergence of this geometric series is r equals 1. Express the function f of x is equal to 1 divided by 1 minus x to the power of 2 as a power series. Exercise 1b. Find the power series representation for the function f of x is equal to 1 divided by 1 minus x to the power of 3. 1-c. Find the power series representation for the function f of x is equal to x cubed divided by 1 minus x to the power of 3. Let's start with exercise 1-a. So let's start with the geometric series 1 over 1 minus x is equal to summation n equals 0 to infinity x to the power of n. Now notice, when we differentiate this geometric series, we're going to obtain, in the denominator, we're going to obtain 1 minus x to the power of 2, which is what we want, because we want to find the power series representation of the function 1 divided by 1 minus x to the power of 2. So that's the motivation for differentiating both sides of this geometric series. So differentiate d dx of 1 over 1 minus x. This is equal to, differentiate the expanded form. So the expanded form of this summation is going to be 1 plus x squared plus x cubed and so on. And this is equal to d dx of the summation form of this, summation n equals 0 to infinity x to the power of n. Now when we differentiate this, we have 1 minus x to the power of minus 1. Let's rewrite it in this way. Apply the power rule and a chain rule. Bring the exponent down, negative 1 times 1 minus x to the power of minus 2. Multiply by the derivative of the inside using the chain rule, multiply by negative 1. If we simplify this, we get 1 over 1 minus x to the power of 2. So differentiate 1 over 1 minus x, and we get 1 over 1 minus x squared, and this is the function for which we want to find its power series representation. So differentiate term by term. The derivative of 1 is 0, derivative of x is 1, derivative of x squared is 2x, applying the power rule, derivative of x cubed is 3x squared, and so on. Now differentiate the summation. Summation n equals 0 to infinity. Bring the derivative inside the summation and differentiate x to the power of n using the power rule. So we get n, bring the exponent down, subtract 1 from the exponent. Now notice n equals 0 doesn't make a contribution to this sum, so we can start the index at n equals 1. So we now have the power series representation of 1 over 1 minus x to the power of 2. In expanded form, this is equal to 1 plus 2x plus 3x squared plus 4x cubed, and so on. In summation notation, this is summation n equals 1 to infinity n x to the power of n minus 1. Now, the original geometric series had a radius of convergence to be equal to 1. So the radius of convergence of this new series is also r equals 1, because we learned earlier that if we differentiate a power series, the radius of convergence does not change. So the radius of convergence of this new power series is still r equals 1. So this is the power series representation of 1 over 1 minus x squared, and we got that by differentiating this geometric series here. Differentiating term by term, and we got the power series of 1 over 1 minus x to the power of 2. And its radius of convergence is the same as the radius of convergence of the original geometric series. Now, part B, we would like to find the power series representation for the function f of x is equal to 1 divided by 1 minus x to the power of 3. Now, to obtain 1 minus x to the power of 3 in the denominator, if we go back to the result in 1a, we have 1 over 1 minus x to the power of 2. If we differentiate that with respect to x again, we're going to get 1 minus x cubed in the denominator. So that's the motivation for differentiating the result of 1-a to get 1-b. All right, so we have d dx of 1 over 1 minus x to the power of 2. This is equal to d dx In expanded form, we have 1 plus 2x plus 3x squared plus 4x cubed, and so on. And this is equal to ddx of summation n equals 1 to infinity n x to the power of n minus 1. All right, when we differentiate this, we have 1 minus x. Differentiating the left-hand side, we have 1 minus x to the power of minus 2. Apply the power rule and the chain rule. So bring the power down, we get minus 2 times 1 minus x to the power of minus 3. Subtract 1 from the exponent. And now apply the chain rule, differentiate the inside, we get negative 1. Simplify, minus 2 times minus 1 gives us plus 2. We get 2 divided by 1 minus x to the power of 3. So we can now write the power series representation of 2 divided by 1 minus x cubed. So 2 divided by 1 minus x to the power of 3 is equal to, let's differentiate term by term. Derivative of 1 is 0. Derivative of 2x, applying the power rule, is just 2. Derivative of 3x squared gives us 6x. Derivative of 4x cubed gives us 12x squared, and so on. Now let's differentiate the summation. Summation n equals 1 to infinity. Bring the derivative inside the summation and differentiate x to the power of n minus 1. Applying the power rule, bring the exponent down. So n minus 1 times x to the power of n minus 2. All right, we now have the power series for the function 2 divided by 1 minus x to the power of 3. But the question was to find the power series for the function f of x is equal to 1 over 1 minus x cubed. So we can simply multiply both sides by 1/2 and get the power series for 1 over 1 minus x to the power of 3. So 1 over 1 minus x to the power of 3, this is equal to, multiply both sides by 1/2, so 1/2 times 2 is 1, plus 3x, plus 6x squared, and so on. Now multiply the summation also by 1/2, we get n equals 1 to infinity, n times n minus 1, times x to the power of n minus 2, divided by 2. All right, so we have the power series representation of 1 over 1 minus x to the power of 3. This is equal to summation n equals 2 to infinity, n times n minus 1, x to the power of n minus 2, divided by 2. And the radius of convergence is the same as the original radius of convergence for the geometric series. So radius is equal to 1, and x less than 1, larger than negative 1. Now, let's look at part C. In part C, we wanted to find the power series for the function f of x is equal to x cubed divided by 1 minus x to the power of 3. This is going to be fairly easy because we can rewrite this function as x cubed times 1 over 1 minus x to the power of 3. But we already have the power series representation of 1 over 1 minus x to the power of 3. That was done in exercise 1-B, and it's this result here. 1 over 1 minus x cubed is equal to summation n equals 2 to infinity, n times n minus 1 times x to the power of n minus 2 divided by 2. So just multiply both sides by x cubed, and we will have the answer. All right, so we found 1 over 1 minus x cubed, the power series representation for this to be summation n equals 2 to infinity, n times n minus 1, x to the power of n minus 2, divided by 2. Now multiply both sides by x cubed. So we get x cubed divided by 1 minus x to the power of 3. This is equal to x cubed times summation n equals 2 to infinity, n times n minus 1, x to the power of n minus 2, divided by 2. Now, we can just bring this x cubed inside the summation, multiply it inside, and we're going to get n minus 2 plus 3, we're going to get n plus 1. X to the power of n plus 1. And the radius of convergence for this power series is 1. So this converges for all values of x between negative 1 and 1. All right, so expanding out this power series, we're going to get x cubed divided by 1 minus x to the power of 3. This is equal to summation n equals 2 to infinity, n times n minus 1, x to the power of n plus 1, divided by 2. This is equal to, so let's plug n equals 2. The first term will be 2 times 1, x to the power of 3, divided by 2. The next term will be plugging n equals 3. So we get 3 times 2, x to the power of 4, divided by 2. Plus, now plug in n equals 4. We're going to get 4 times 3, x to the power of 5, divided by 2, and so on. And the radius of convergence of this series is r equals 1. That means this series converges for all values of x less than 1, larger than negative 1. All right, let's do some summary. So basically, we started with the geometric series 1 over 1 minus x is equal to summation n equals 0 to infinity x to the power of n. We differentiated twice to find the power series for the function f of x is equal to 1 over 1 minus x to the power of 3. And then we multiplied by x cubed to find a power series representation for f of x is equal to x cubed divided by 1 minus x to the power of 3. And in all our calculations, in 1a and 1b and 1c, the radius of convergence does not change because the original geometric series had a radius of convergence of 1. The new power series that we obtained by differentiating the original geometric series has the same radius of convergence. So it converges for all values of x less than 1, larger than negative 1. All right, thanks.